sum up these loop amplitudes. You take the amplitude, but then you want to expand in 1 over MW. It's kind of a weird thing to do from the gauge theory point of view. There's a good reason why, well, there's a reason why people don't usually think about that kind of expansion, because it's not really very useful in other dimensions. 6th dimension somehow is special for this purpose. Let me explain this. It's kind of a funny point. So let's say you have some, if I restrict myself to the scattering of the massless gluons on the Coulomb branch. So remember, I'm going to this point on the Coulomb branch where the vectors have this zk symmetry. All the vectors are non-zero, have zk symmetry. Then there's no tree-level scattering of these bosons. So they scatter starting at one loop through the exchange of the loop of the W boson. So I have some one loop diagram like this of these U1 to the k-1 photons, and then have the W bosons running the loop. So of course you can calculate this loop integral by, there's some integrand and you have some massive propagator. Now, each time you increase your loop order by 1, so each time if you increase loop order by 1, let's say, adding let's say a W boson propagator, you'll be, generically you'll add 3 extra propagators and add the one loop integral. So you have an extra, roughly speaking, d6, and in 6 number d6p over 1 plus p squared plus mw squared cubed. So whatever integral answer you get in the end, when you expand in 1 over mw, you actually get the same set of kind of ordering in 1 over mw, the expansion. Okay, this thing doesn't scale with mw. And so, I mean, if you have been working in, say, 4 dimension, have the 4th p, then this thing goes like 1 over mw squared. So you go to higher and higher loop order, you will also have, the amplitude will go like higher and higher powers of 1 over mw. But in 6 dimensions, all the L loop order amplitude will start the same order in the 1 over mw expansion. But that's kind of peculiar. But that's what we expect, actually, from the string theory side, because on the string theory side, at every loop order, we expect to have leading order 1 over mw squared term plus on the tree level string amplitude, and that should match on with this expansion. Okay, so from this duality, one expects some kind of miraculous relation between this alpha prime expansion of tree level string amplitude and the leading term in the 1 over mw expansion of the L loop Yang-Mills amplitude for all L. Now, that couldn't possibly make sense in cyclic Yang-Mills theory, you might say, because this cyclic Yang-Mills theory is going to diverge at some loop order. And that is true. In fact, if you can compute the general non-abelian gauge boson scattering amplitude in that 60 gauge theory, the first divergence show up at 3 loop order. But it turns out that, in fact, if you look at the scattering of the gauge bosons just in the U1 to the k-1 Cartan subalgebra, then the 3 loop divergence is not there. The first place where it diverges is at 4 loop order. So at least up to 3 loop order, there's a sensible finite amplitude in the 60 Yang-Mills theory. You can ask, do those amplitudes agree with the combination of double scale string theory? Let me emphasize that here, there's kind of a non-trivial set of data to on both sides. These for the 4-point amplitude, the kind of polarization, the space-time polarization dependence is all trivial, it's fixed by the tree level. But there's going to be some non-trivial dependence on the color assignment in this Cartan. So on the 4 legs, you can choose different U1s. And then there's some momentum dependence. Of course, the momentum dependence is relatively simple at any given order alpha prime, but nonetheless, there's some dependence. We look at these different dependence on STU minus n variables. At one loop, this agreement between the 2 sides was found in 2003 by Aharoni, Kutasov, Fial, and Sahakian. There they used a kind of, there they were just interested, so the one loop amplitude in the gauge theory, just naively would like to match on this with the leading order term in the tree level amplitude from the Liu string theory side. If one is just interested in the leading order in alpha prime expansion, those authors have some very clever way to relate that string amplitude computation to some n equals 2 string amplitude, and they're able to calculate this without having to directly integrate conformal blocks. And they found that that leading order term in alpha prime expansion agrees with the one loop answer in the gauge theory, which is already very non-trivial, actually, because it has some non-trivial dependence on the color assignment of external x. But of course, it will be completely miraculous if this would always also work at two-loop order, it seems, because the two-loop computation is much more complicated, and the three-loop is much more complicated. In order to go to higher order alpha prime expansion, we need our, the only way we know how to do this is through the direct integration of conformal block, which is what we did. So one can compare that with a two-loop computation, the gauge theory side. So if you do this, so in the two-loop we have diagrams like this, and diagrams like this. Now, of course, as we have heard several times in this workshop, the direct Feynman diagram computation of this two-loop amplitude is pretty much impossible. One has to use the unitarity method, and thankfully, the hardworking amplitude people have told us how to do this, and we take their method, and all we need to do is to put in these massive propagators for the W bosons of various W boson masses. So on the Coulomb branch, the W bosons come from this, the W bosons, let's say, stretch between this, let's say 1, 2, 3, 4, 5, 6. The W boson stretch between the first and third brain would be, this is D1 brain stretch between NS5, will be the mass will be proportional to this length, which of course you know. So we put in that information, and then you can calculate this amplitude. Let me at least describe briefly how this computation is done. Well, in fact, for this, we need to use the 60 spinor helicity formalism, which is developed by Yutting and company, Den and Siegel, and also by Chang and Ocano, spinor helicity variables. So here, if you have a 60 non-momentum, P, you can write in bispinor notation PAB, where AB are these are the SO 1,5 spinor indices. And there's a P lower AB, which can be just written as 1/2 epsilon ABCD, P upper CD. So this can be written in the form lambda, so for non-momentum, lambda A little a, lambda B or little a contracted, where this A, well, let me say that in a second, and this can be written as lambda tilde A, lambda tilde A dot, lambda tilde B little a dot, where A and B dot, these are the SO4, or SU2 times SU2, little group index. So here, unlike in four-dimension scalar amplitude, where you can label the states or masses particle with plus and minus helicity, here the helicity really represents a representation of SU2 times SU2 little group. So here you have to specify this representation with back to the times SU little group. So you can think of this little a and little b dot, or little a and little a dot, as the internal little group index, whereas the capital A, capital B, these are the space-time spinor indices. And then one for the maximally supersymmetric gauge theory, it's convenient to work with supermomentum. Supermomentum. These are fermionic objects which you obtain by combining these helicity variables lambda a with some Grassmannian variable eta a, and also eta tilde a dot. So this I call it q upper a, and there's a q tilde b, which is lambda tilde b dot eta tilde b dot. In terms of, so a super amplitude will be expressed as some function of the super momentum, and you expand that function in these eta tilde variables, then you can read off the amplitude involving the various particles in various sitting in various components of the super multiplex: scalars, fermions, vector bosons. The tree level amplitude is well, if you had a tree level amplitude in such a theory, it will be some. I should write on a different board. So the color ordered within the 60 supernomials with general assignment of external legs, color ordered tree amplitudes, a tree with 4 external legs, has a very simple compact expression in terms of the super momentum. Over some S12, S23, these are Mendelssohn variables. Sij is minus pi plus pj squared for the P1, P2, P3, P4 momenta, external x. The Grassmannian delta function I from 1 to 4, sum of these qi. So for each external particle labeled by I runs from 1, 2, 3, 4, there's a qi, comes with a lambda I and the eta I. So this this Q has otherwise 8 components, which is why I write delta to the 8th. And this Grassmannian delta function is just really just the same thing as the product of these Grassmannian super momenta. If you expand this out, you get some polynomial expression that's 8th order in the eta variables. It could involve, for example, if you look at, so there's eta 1, eta 2, eta 3, eta 4, each comes with some eta A or eta tilde B dot. So here, if you collect, let's say, for the ith particle, if you collect a term in this amplitude that looks like, say, proportion either 1 or eta I squared or eta I tilde squared. The square means eta I A, eta I lower A, eta I upper A, eta I lower A, similar for eta I tilde, or eta I squared, eta I tilde squared, even number of etas. In this case, you'll get an even number of etas, or eta squared or eta tilde squared. Then these are the scalars in the super multiplets. If you have eta I A, eta I tilde B dot, then this will give rise to a vector boson. So by expanding this amplitude, you easily figure out the by explaining the super amplitude, you easily figure out the actual scattering amplitude of the various bosons and scalars and the vector bosons and also the fermions in the amplitude. But of course, for us, we're interested in, so this is a color order amplitude without putting in color factor. Putting in color factor, this tree level amplitude is 0 for us because we are restricting to those gluons in the Cartan of the SUK. So for us, the amplitudes of interest are the loop amplitudes starting at one loop. So at one loop, it's known that this amplitude can be reduced to the unitarity method to scalar box integral. So you have minus S12, S23, tree amplitude times some color factor, C1234, times this. By this diagram, I mean the scalar box integral. Just integrate with one 6-dimensional momentum with these propagators, plus the two other terms with the 2-3 exchanged and 3-4 exchanged. Now this was originally written, I guess, first probably for superconformal, this kind of theory, where you have massless propagators. But you can also replace this massless by massive propagators. You can argue that either based on unitarity methods, or you can try to study this amplitude in higher dimension and think of assigning some non-zero. I mean, you start with some amplitude, say, in, first of all, I mean, this kind of works in general dimension, and I guess it will be useful to think of this as coming from some computation in, say, 8 dimension, and you put in, you assign some kind of some non-zero momentum of the internal leg of the internal propagator in one of the transverse dimension to a 6th dimension, so that effectively gives you a mass. But anyway, the upshot is that for us, even though we have this exchange of the massive W boson in the loops, this formula still apply, and all you need to do is to replace the massless propagators by the massive propagators with the appropriate W boson mass. So that's all you need to do. So put in the W boson mass. And remember, the W boson masses are non-trivial. They depend on the separation of these, which depend on the angles. But you can do that. And then at two loop, the amplitude can be expressed in terms of similarly color factors times the scalar loop integral that involves loop diagrams like this and this, which one can calculate numerically. Well, I mean, for us, we are really just interested in expanding to first order in 1 over mw. We're interested in expanding this amplitude to order 1 over mw squared. For instance, over here, we have this integral d6p. d6p, 1 over p squared plus mw squared to the 4th, roughly. Then expanding this out, you would get 1 over mw squared. And then you have higher order terms in 1 over mw that's also proportional to more powers of STU variables. Similarly, here you can also expand. And if you are powerful enough to calculate the genus 1 string amplitude, you can compare with 1 over mw to the 4th. We were only able to calculate tree level so far, so we can compare that with 1 over mw squared for these. And after some work, after sorting out all the errors in the Mathematica file, we managed to get these to miraculously agree with answer from double scale little string theory to 4 digits. In the case of, so that's pretty convincing. K equals 2, 3, 4, 5, and all possible assignments of values of L. You remember that corresponds to labeling the choice of basically which U1 these gauge fields are in. For the amplitude that involves, so basically L, and minus L, minus L. This L, well, anyway, L labels the charge back to this ZK tilde that permutes this K as 5 brands. So get some non-trivial numbers, and they agree to a good precision, numerical precision with answer from safety gauge theory. So what does this mean?
Sorry, so the K appears as inside of W, both the mass?
K is the rank of the gauge group, SUK.
So how does it appear in the amplitude?
The way the amplitude is that W1 mass depends on, for example, depends on.
So that's
depends,
okay.
Yeah. But I mean, the possible assignment of L also depends on what the value of K are. So this L ranges from 0 to K minus 2, for instance, in my convention. Okay. So what does this mean? It wasn't, when we started on this project, it wasn't clear that they were going to match. In fact, I was in the middle, halfway through the project, I was very depressed because so we're doing this very hard computation, and the result probably just won't agree because we're comparing quantities in different regimes. So the double-scale little string theory, perturbatively, really describes the physics far away from the origin of the Coulomb branch, whereas this 60 gauge theory, particular computation is supposed to be a priori really only meaningful, if at all, near the origin of the Coulomb branch. In fact, as I said, this amplitude is supposed to, if you go to the next loop order at 3 loop, you still have some well-defined finite amplitude, and there's a big question mark whether they will agree. I'll come to that in a second. But at 4 loop, there's a non-trivial, there's a non-zero UV divergence, logarithmic divergence, which means that your gauge theory description is simply incomplete. And if you understand your rule of how to add these higher dimension operators that completes the theory, you will be able to have some, you should have some well-defined amplitude at that order. But it was not really clear how to do this from the 60 gauge theory point of view. On the other hand, the double-scale little string theory has a completely well-defined alpha prime expansion. We can just go and, anyway, these things are completely well-defined, and we can calculate these numerically. And the question is, so, why do they agree with, why would they agree at 2 loop order, and why do they not agree in higher loop order, and what can you do with that? Now first, let me first make some comments on the higher dimension operators that can correct the 60 Yang-Mills action. If you take the Yang-Mills action, super Yang-Mills action, and add some higher dimension operators, a priori, if you look at the low energy theory from the little string theory at the origin that corresponds to this most strongly coupled little string theory, you can possibly have higher dimension operators that are compatible, any operator that's compatible with 60 supersymmetries. Such operators are classified. So there's some operator. There's a single 1/2 UPS operator, which is a form trace after the 4th. This is a standard one this is the kind of operator that will appear in the kind of Bohr-Infeld deformation of Yang-Mills theory. And then there's a quarter BPS double trace operator of the form d squared trace squared after the 4th. I just write schematically like this at this order. So this is dimension 8 operator. This is here a dimension 10 operator. That's a quarter BPS. There's also a non-BPS, sort of D-term operator, single trace form d squared after the 4th, and write schematically like this. I mean, it's a supersymmetric completion of this, of course. Now, this is an operator that's kind of that will supply that should supply the counter term to the 3 loop UV divergence of the non-abelian gauge theory at the origin of the Coulomb branch. But this operator turns out to vanish when restricting to the Cartan subalgebra. So, and if you actually work it out, it always involves some commutators that just vanish when you restrict to the U1 to the K minus 1. So if you restrict the Cartan, so there's some arguments indicating that these operators are going to be protected and UV finite, which essentially explains why the amplitude when restricted to the Cartan vanishes, is free of UV divergence at 3 loop order because there are no available counterterms to these operators. But going to a 4 loop, you would have the counterterms of the next order, which will be of dimension 12. So let's say d to the fourth f to the fourth, there'll be some there'll be some operators at dimension 12 that does not vanish when restricting to the Cartan subalgebra. And also, these are non-BPS, these are D-term operators, which would be counter terms for the for-loop divergence that is there. That is there even when you look at amplitudes of the Cartan gluons. So you can make such statements, but this still doesn't help us understand why these Coulomb branch scattering amplitudes do match at two-loop order. Now, tentatively, there might be an explanation of the following sort. So here, we're looking at, if you, instead of thinking about the theory, the non-abelian theory, at the origin of the Coulomb branch, but you just look at the abelian effective action on the Coulomb branch, you could consider, you could ask, what is, from this amplitude, you should be able to extract the abelian, you want to the k minus 1, abelian effective action on the Coulomb branch. So the amplitude, like this one loop, this will be responsible for, if you expand to, say, order 1 over mw squared, f to the, this will have to do with terms like this, 1 over mw squared, f to the fourth, which should really be completed into, if you, this mw is basically the vev of the scalar. So this should really be completed to a term in the Coulomb branch effective action of the form, let's say f to the fourth, 1 over r to the fourth, where r is the distance, the expression in terms of vev of the field, away from the origin on the Coulomb branch. And similarly, if you have some two-loop amplitude, you might have some term like 1 over r squared, d squared f to the fourth, and so forth. And if you have a term like d squared f to the fourth, generally the coefficient could be some function f of r. And a priori, what one might expect is that by comparing, if you didn't know that the Sigma-Yamio's amplitude agrees with double Taylor string theory, you would say that by comparing the calculation of these limits, f of r will go like some 1 over r squared near the origin, and go like 1 over r squared at large r, but the coefficients may not agree. There could be some non-trivial interpolating function. But here we see some evidence that they might agree, and that f of r would just go like 1 over r squared. So it might be possible to prove a non-renormalization theorem along the same line as the work of Sethi, Stern, and Parban some years back, where they studied these in the context of BFS matrix theory. They were able to prove some non-renormalization theorem of this sort for 6 derivative terms in the matrix theory effective action. And this is also of the same type as 6 derivative. So it's likely that by rewriting their argument, one can probably prove a non-renormalization theorem that will explain this agreement. On the other hand, if you go to the next order, which is 3-loop, and that will have to do with the kind of dimension 10 operator of the form, dimension 12 operator of the form d to the fourth f to the fourth on the Coulomb branch, and that's kind of like a derivative term in the Coulomb branch effective action. And our experience in other dimensions suggests, including 0 plus 1 dimension, was a famous story in the context of BFS matrix theory that there's no non-renormalization property of the v to the 8th, the a derivative term on the Coulomb branch effective action. And that actually had caused quite a lot of confusion in the early days of matrix theory. Here we may not have a non-renormalization property for the a derivative operators. So if you calculate these 1 over mw squared, if you calculate, go to the next order, the